All right, today's topic is asymptotic analysis. Now, last time we did statement execution counts and we saw how to analyze a loop, how to count how many statements execute in a loop. And today we're going to carry it one step further and see how to use this information asymptotically for very large values of n. So you know what the asymptote is of a graph. You know it's when x gets really, really big and it asymptotically approaches. So we're talking about large values of n. That's what asymptotic analysis is about. Now this material, I know many of you have seen before because this is actually some material that you should have seen in discrete structures, which is a co-requisite for this course. And so here again, this should be reviewed. Go ahead. So we will begin with posing this question. Suppose you have algorithm A and you do a statement execution count and it's f dot n equals 25n plus 93. And algorithm B, you do a statement execution count with that one and it's f dot n equals 2n squared plus 4n minus 3. And the big question is, which one of these is better? Like if you were a customer, would you rather buy, yes. Yeah, actually, it's a little bit of a trick question because it does depend on n, right? So if you plot this, if you graph this, here in figure 3.5 in the book, there's a plot of 25n plus 93 and 2n squared plus 4n minus 3. Now what is the y-intercept of f dot n in algorithm A? The y-intercept. It's 93. When n is 0, y is 93, right? Okay. And what's the y-intercept for algorithm B, what's the y-intercept? It's negative, it's negative 3. So what happens is, in this region between 0 up to about, what's the crossover point? It looks like 10, maybe, 13 or something like that, somewhere around there. So in this region for small n, which one is worse? Oh, sorry, let me rephrase that. Which one is better? The 2n squared plus 4n minus 3. But what happens is there's a crossover point, and for large values of n, ultimately 2n squared plus 4n minus 3 is worse than 2n plus 93. Does everybody see how that works? Now, as a customer, are you more interested in how fast your program runs for small problems, or are you more interested in how fast it runs for really big problems? Yeah, really big ones. So that's the area that we're interested in. That's why the asymptotic analysis is for the situation when n gets really, really big. So the tools that we use, the analytic tools that we use, are these asymptotic upper bounds and asymptotic lower bounds to determine the performance of the algorithm. Okay, and you remember here, this is from discrete structures, right? So, but for those of you who are just taking it now, this might be a little new. So let's take a look at what the first definition is called big O. And big O is the definition of the asymptotic upper bound. And what we have here is the formal definition of what the upper bound is, what big O is. And basically, big O is a set of functions, right? And here's the formal definition. So let's see if we can parse this formal definition. So you see it starts with an open brace and ends in a closed brace. So it's a set. And it is a set of functions f dot n, right? Now, what is this backwards E? There exists. So there exists a C and an N naught, and what does it say about C? C is greater than what? 0. And N naught is greater than what? 0. So that means that C and N naught are both what? Positive. Another way of saying that, right? So there has to exist positive constants, C and N naught, so that's the range. And then in the body of the quantification, there is another quantification for all n, and what is the restriction on n? N has to be, n is greater than or equal to what? N naught. But what was n naught? N naught was was positive, right? So for all n greater than this positive constant, what has to be true? And the key one here is f dot n is less than or equal to c times g dot n. All right? So this defines that set of functions. And what we're going to do, what we need to be able to do in this course is we need to be able to compute, we need to be able to prove that a function is big O of another function. And this definition is the key to the proof. So this individual steps of the proof are easier to understand maybe than this formal notation. And so that's what we will do. And then we have this curious notation. Even though this is a set of functions, what we're going to say, this O notation, is that f dot n equals big O of g dot n. That just means that f dot n is in the set. Because strictly speaking, f dot n is a function, and how can a function be equal to a set of functions? So mathematically, strictly mathematically, that is not type correct. You know, the fact that f dot n is big O of g dot n. Okay, but this is very common computer science terminology. When in computers, you know, when you do read about analysis of algorithms, they'll say f dot n equals big O of g dot n. Well, that really means that f dot n is an element of. In fact, that equals. Actually, I've seen some people are starting to do it more accurately. They're starting to say this: f dot n is an element of big O of g dot n. All right. So this is what but we will follow the majority of people and just put an equals here instead of is an element of. All right. Now, yeah, question?
So the
big O, yeah.
Is that means the upper bound, right?
No, this big O is that set. That big O is that set. It is that big O. It's a set of functions. Mathematically, it is a set of functions. Okay. I think what will happen is let's see how to use this definition to prove big O. Functions are big O. And then we'll do an example of how it relates to the sets of the functions in a bit. All right? Okay, so now let's do some really simple examples. Let's take those first two examples that we use and let's prove that it's big O. Now, do you guys remember how to do this, those of you who have had discrete? What we want to prove is that 25n plus 93 is big O of n. Now, there's always a statement that you must write down before you prove something is big O, one function is big O of another function. There's always a statement that you have to write down. It's kind of like in proof by mathematical induction, there's always, you know, the statement that you have to write down for the induction case. So, coming back to this definition, what do we have to write down? We must prove that there does what? Yes, we have to write down that there exist positive constants, c and n naught, such that, and then 25n plus 93 is the function on the left, and then is less than or equal to c times n, and c times n is the constant times the function that's in the big O parentheses. All right, so does everybody see how to set that up? So coming back to here, to the previous slide here, you see it's what we're saying is that it's this part. F dot n is less than or equal to c times g dot n. So in this case, our f dot n is the what? Oops. Our f dot n is the what? 25n plus 93, and the g dot n is n, and so it's 25n plus 93 is less than or equal to c times n for n greater than or equal to n naught. Is everybody clear? So this is what we have to prove. All you have to do is just write this down at the beginning and then just do it. So let's do it. Now, do you remember how we did this? Which side did we start with? The right-hand side or the left-hand side of the inequality? Yeah, we always start with the left-hand side. So we start 25n plus 93. Now, what we have to do is prove that this is less than or equal to what? C dot n. So we do this step by step by step, and we give a reason for each step, right? In the equational style. Okay. So remember, you guys remember how to do this? it's less, yeah, it's less than or equal to, what is 25n? We need to get it with just a c times n, so somehow we got to get rid of the 93. So what can we do with the 93? We have to replace the 93 by a larger value. So how can we replace the 93 by a larger value? We replace 93 with a larger value by multiplying it by what? Or sorry, by replacing it by what? By n. But now, 25n plus 93 is less than or equal to 25n plus n, only provided that what? Yeah, only provided that n is greater than or equal to 93. Is everybody clear on this step? That is true. Isn't 25n plus 93 less than or equal to 25n plus n, provided n is greater than 93? You're replacing 93 by something that's bigger than 93, right? So, but now what can we do? Some math, and what is 25n plus n? 26n. But now we wanted to get this to be less than or equal to what? C times n. So as long as c is what? What does this equal? This equals, provided c equals 26, this equals what? C times n. But now what did we have to prove? We had to prove that there exist what? Positive constants c and n naught. Well, so what are those? So what did we prove? As long, provided that what? N is what? Greater than or equal to 93, and provided that c is 26. So therefore, what can we conclude? We have shown the existence, what? 93. So c equals 26, and then not, and we have, is all we have to do is show the existence of those constants. And we did it. Right? By construction in this proof. Is everybody clear on how that worked? Okay. So let's do another one. How about 2n squared plus 4n minus 3 is big O of n squared? Now, what do we have to write down first? There exist what? Positive constants. What are they? C and n naught, positive, such that
2n squared plus 4n minus 3.
Yes, 2n squared plus 4n minus 3 is greater than or equal to cn squared.
For n naught is greater than or equal to.
For n is greater than or equal to n naught. Okay, so here it is. Here's the statement we have to write down. Let's prove there exists positive constants c and n naught such that 2n squared plus 4n minus 3 is less than or equal to cn squared for n greater than or equal to n naught. Are we good? And what side do we start with? Left-hand side. So 2n squared plus 4n minus 3. Now, what can we do with this minus 3 hanging out here? Yeah, don't you agree that if we eliminate this negative value, that 2n squared plus 4n minus 3 has to be less than or equal to 2n squared plus 4n? Now, is everybody... Every single step is logical, right? So everybody agree that 2n squared plus 4n minus 3 has to be less than or equal to 2n squared plus 4n. Because if you subtract 3, and you don't subtract 3 anymore, yeah? Is everybody good? Okay, but now what about this 2n squared plus 4n? Because we need to get it with an n squared. So somehow we've got to change that n to an n squared. That 4n, we've got to get it to an n squared. So how do we do that? Yeah, replacing 4n with the largest value. So if we multiply that 4n times n, then 2n squared plus 4n is less than or equal to 2n squared plus 4n plus 1. Oh, sorry, 2n squared plus 4n times n. Now look, this doesn't work if n is a half. If you multiply 4n times n and n is a half, then you're not making 4n bigger, you're making it what? Smaller. You're making it smaller. So this is only true provided n is greater than or equal to 1. Is everybody clear? Okay? But now what's 4n times n? 4n squared, and what's 4n squared plus 2n squared? 6n squared. All right. So with some math, that's 6n squared. But now we wanted to get this to be less than or equal to what? Cn squared. So now what? C must be 6. Yeah. So this Well, provided c equals 6, this is cn. We do have 2n squared plus 4n minus 3 is less than or equal to cn squared. And so now what's our provision? Now we have determined the constants. And so what constant did we determine for c? C is 6, and n naught is 1. And that comes from this proviso that we had to assume that here, right? On this step, replacing for n with a larger value, provided n is greater than or equal to 1. So provided n is greater than, so if n naught is 1, then we have proved that this is, that 2n squared plus 4n minus 3 is less than or equal to cn squared for n greater than or equal to n naught. Yeah, question?
I don't know if this is like important necessarily, but like if n was a negative number,
that is a good question.
still increase it?
Yeah, hold on. That is a good question. And remember, we said must prove there exists what did we say? Must prove there exists what?
Positive.
Constant c what? C and n naught. So n naught has to be positive. And furthermore, we're proving it for n greater than or equal to n naught. So that takes care of that. So negatives aren't part of the proof. I mean, negatives are excluded explicitly by this definition. Are you with me? Because look, n is a measure of how big the problem is. So n could be like the number of data values that you're sorting, and you can't have like a negative number of values. You see what I'm saying? So that's why this includes in it the positive. Okay? And so our conclusion then is we have proved that if c equals 6 and n naught equals 1, we have proved that 2n squared plus 4n minus 3 is less than or equal to cn squared. And there's those positive constants, so they exist. We show by construction that those constants exist. Now, on the other end of the bound is a lower bound. Now, what we proved were upper bounds, and upper bounds are denoted by this slanted big O. So big O is upper bound. On the other hand, what is this letter?
Omega.
Omega. This is lower bound. And we look, again, it's a set of functions. But the only difference is now, before we had c times f of n, no, sorry, before we had, what did we have before? Right, we had f dot n is less than or equal to c times g dot n. Right. This time it's switched. The order is switched. So now let's do an example of a lower bound. So 25n plus 93 is bounded below by n. Okay, it's big omega of n. So now what's the statement that we have to write down to start our proof? Well, what do we have to write down? We have to always write down the statement before we actually demonstrate the proof. Prove there exists a what? A positive constants. What are they? C and n naught. Not n, but n naught. Okay? Such that what? Now such that 25n plus 93 is what? Above is greater than or equal to c times n. So here it is. Must prove there exists positive constants c and n naught such that 25n plus 93 is greater than or equal to c times n for n greater than or equal to n naught. And what side do we start with? Left-hand side. Always the more complicated side. The bound is always just a single term in practice. I mean, not necessarily mathematically, but in practice. So we start with the 25n plus 93, and we have to show that this is greater than or equal to something. Yeah, constant times n. So now this is an interesting situation. We can just drop that 93, right? Because isn't it true, because 93 is a positive value, that 25n plus 93 is greater than or equal to 25? Makes sense? Are we good? But now look, it's already 25n. We wanted to get c times n, so provided that what? So yeah, so equals, provided that c equals 25, c times n. So now here's an interesting scenario. The thing of it is that so we know that c is going to be what? 25. But what about n naught? Were there any assumptions that we had to make in order to prove this? I mean, were there any provisos that we had to invoke? Yeah, so that means that any n naught will do. So c equals 25, but now by convention, our convention is going to be that if any positive n naught is possible, we'll just always pick n naught equals 1. All right, because you got to pick one to show that it exists. All right. Is everybody clear on this? Remember that situation? Okay, let's do 2n squared plus 4n minus 3 is bounded below by n squared. So now what do we have to write down? There exists positive constants c and n naught such that what?
2n
squared
plus 4n minus 3 is greater than or equal to n squared. C times n squared for n greater than or equal to n naught. Okay, so here it is. Must prove there exists positive constants c and n naught such that 2n squared plus 4n minus 3 is greater than or equal to c n squared for n greater than or equal to n naught. And which side do we start on? The left. We're trying to get this to be greater than or equal to cn squared. So how can we do that? What can we do with this negative 3? Yeah, we can make it more negative. So we can multiply it, so we can multiply it by n. So the reason we say 2n squared plus 4n minus 3 is greater than or equal to 2n squared plus 4n minus 3n, because we're multiplying 3 times n, and provided that n is greater than or equal to 1, we're making that a more negative value. And the reason we do this manipulation is so that we can combine the n. We need to get these lower order terms to meld into the highest order term. You know, the whole idea is to get it to the highest order term with the inequalities, using the properties of inequalities along the way. And now what's 4n minus 3n? So equals by math 2n squared plus n. But now we still got to get this to be greater than or equal to something. So a constant times n squared. Got to get this greater than or equal to a constant times n squared. So, provided eliminating a positive value, we can eliminate that positive value. And how do we know that n is positive? Provided that what? Greater than or equal to 0. So we'll put that proviso in our proof. All right. And now, so this is greater than or equal to 2n squared. So now what? Provided that c equals 2, cn squared. And now comes an interesting little scenario. We know that c is going to be 2, but what about n? Because in one step it said provided n is greater than or equal to 1, and another step it said provided n is greater than or equal to 0. You have to do the stronger one. Suppose you had a proviso that said suppose you had a proof and that said provided n is greater than or equal to 25, and then suppose somewhere later in the proof it said provided n is greater than or equal to 50. Then which one would you pick? Yeah, you would pick the stronger one, which is n is greater than or equal to 50, because if it is greater than or equal to 50, then what? It's greater than or equal to 25. So you got to pick the stronger one. So here what would we pick? N is greater than or equal to
1, yes. Does everybody see that? So it's the stronger one. So c equals 2 and not equals 1. Does everybody? Yes.
So didn't we just prove that that same function is bounded above by n squared?
Oh my goodness, what a great observation. We did just prove that this was bounded.
So what does that mean?
Above and below. Oh man, I couldn't have paid you to ask a better question. Hold that thought. Yeah, that was a very interesting observation. So hold that. Well, I want to do a couple more techniques. Some situations on this lower bound can be a little tricky. And I don't know if you remember this, but there's some particular kind of little tricky techniques that we have to use in our proofs for these lower bounds. So here's going to illustrate one technique. Suppose we want to prove that 6n cubed minus 7n equals big omega of n cubed. Now what's the statement we have to write down? There exist positive constants, C and N naught, such that
6n cubed
minus 7n
is greater than or equal to Cn cubed
for n naught. Okay, so it must prove there exists positive constant C and N naught such that Cn cubed minus 7n is greater than or equal to Cn cubed for n greater than or equal to n naught. Now let's just follow those techniques that we had done before. We start with Cn cubed minus 7n. And now what happens? Now what do we want to do? We need to show that this is greater than or equal to something, right? So we can't just drop the 7n. Do you see what I mean? Well, but if you multiply it times n squared, you're making it more negative.
I would want it to not be.
And this has to be greater than or equal to something. So do you guys remember the technique? Now look, here's where it gets tricky. You see this 6n cubed? Subtract 1 from 6 and make it 5n cubed minus nothing. Now what's really interesting about this technique is that what you can do is if you get us into a situation where you have a high order term minus a constant times a low order term and you're trying to prove a lower bound, you can't just drop the negative one. You take the coefficient of the highest order term and subtract 1 from it, and then what you do is you do the computation inside the hint that proves that 6n cubed minus 7n is greater than or equal to 5n cubed. So now do you remember this? We subtracted 1 from 6 and made it 5, and now what we're going to do is we're going to see under what circumstances 6n cubed minus 7n is greater than or equal to 5n cubed, right? So this is what we want to prove. Look, the first step inside the hint. The first step inside the hint is 6n cubed minus 7n is greater than or equal to 5n cubed. That's what we're trying to prove, right? We have to see under what circumstances this is true. But look, now that it's 6n cubed minus 7n is greater than or equal to 5n cubed, what can we do with math? Take the 5n cubed what? To the left, and take the what?
7n.
The negative 7n to the right, and what do we have?
N cubed is greater than or equal to 7.
Yeah, and now we've finessed it. So now we have n cubed is greater than or equal to 7n. Are you with me? And as long as n is positive, we can divide out both sides by n and not change the order of the inequality. So n cubed is greater than or equal to 7n means what? N squared is greater than or equal to 7. And as long as we take the positive square root, what do we have? N is greater than or equal to root 7. So do you agree? Doesn't this prove that 6n cubed minus 7n is greater than or equal to 5n cubed, provided what? N is greater than or equal to positive root 7. By construction. See, this is a constructive proof. Right? But now it's 5n cubed. So now what? Equals provided what? C equals 5, Cn cubed. So what's the C? And what's the n naught? Root 7. Yes?
So only like the last part of that chain of things is the proviso.
Yes. Yes, because we started, yes, and inside the hint, we started with the thing that we were saying, that we claimed. We claimed that 6n cubed minus 7n is greater than or equal to 5n cubed. Well, if we claim that, provided this is true, that is true. Yes. Is everybody good? Now there's one more little one. So that's one technique. Let's take this one step further. What do you think about n cubed minus 5n is big omega, is bounded below by n cubed? This time we can't do that technique quite the way we did it before, because look, we must prove that there exists positive constant C and n naught such that n cubed minus 5n is greater than or equal to Cn cubed for n greater than or equal to n naught. And now we start with the left-hand side. But now, what did we do before? We subtracted 1 from the coefficient. We made the 6n cubed, we made it 5n cubed. But now what's the coefficient of n cubed? 1. So we can't subtract 1, we get 0. So look, here is a fact. C must be positive, but it's allowed to be less than 1. C must be positive. But it is allowed to be less than 1. So now instead of saying that, you know, we had 6n cubed and subtract 1 and make it 5, now what are we going to claim? We are going to claim that n cubed minus 5n is what? Is greater than or equal to 0.5n cubed. Is everybody good? Are you with me here? 0.5n cubed. So now what do we have to show? We have to show under what circumstances what? N cubed minus 5n is greater than or equal to 0.5n cubed. So what's the first step in our hint? What we just said. N cubed. And so now when we take the 0.5 to the other side and the negative 5n to the other side, what is it?
5n cubed is greater than or equal
To
oh, well, I think
point. Yeah, let's take the 0.5n cubed, 0.5 to the left, and then we'll take the negative 5n to the right, and what do we have?
0.5n cubed is greater than or equal to 5n.
5n. And now, multiply both sides by what? 2. Right? So 0.5 times 2 is 1. 5 times 2 is 10. And then you can divide both sides by n because n is positive and not change. So n squared is greater than or equal to 10. So therefore, n is greater than or equal to root 10. Are we good? And so what is our c? Provided c equals 0.5, and that's c n cubed, so c is 0.5 and n naught is root 10. And now we get back to your observation.
Oh, I forgot about that.
Yeah. So now that's a key concept. It's possible for a function to be bounded both above and below by the same function. And why is that? How can that be possible? Because the constant c can be different. We'll show you a little graph of that. So here is the formal definition of big theta. Okay, so big O means bounded above, big omega means bounded below, and big theta means bounded both above and below. So it is an asymptotically tight bound. It's called a tight bound. If it's bounded above and below by the same function. All right. So here's the definition. Now formally, you have to show that there exist two constants, C1 and C2, and one n naught. And so here's the, and so you have it, you see it's bounded below. C1 times G dot n is less than or equal to F dot n, and F dot n is less than or equal to C2 times G dot n. Two different constants. But you know there's a theorem that we use that says that F dot n is big theta of G dot n if and only if it is both bounded above, both big O, and bounded below, big omega. All right? Is all this familiar? You guys are, I see a lot of good heads nodding, and we did this in discrete. It's actually the exact same material, I think. You probably even recognize the functions. And so as an example, we showed, and like you pointed out a minute ago, we showed that 25n plus 93 is big O, and it's also big omega, therefore it's big theta. We also showed that 2n squared plus 4n minus 3 is big O of n squared, and also big omega of n squared, so it's big theta of n squared. And here is an interpretation of it with this function 2n squared plus 4n minus 3. So what happens is, you see there's all these crossover points below n equals 1.0. And if you graph 2n squared plus 4n minus 3, what's the y-intercept of 2n squared plus 4n minus 3? It's negative 3, right? When n is 0, y is negative 3. And it's a parabola. It goes up parabolically. But now, when we had... But now, what is a graph of just n squared? It's a parabola, right? That goes... And what is its y-intercept? 0. Well, the constant for the upper bound was 6. C was 6. And the constant for the lower bound was 2. So what happens is, if you plot 6n squared as a parabola and 2n squared as a parabola, beyond n equals 1.0, you see this blue curve is bounded above by 6n squared and below by 2n squared. So it goes up parabolically. Now, we didn't actually mention this, I don't think, last time, but remember when we said that we determined that an algorithm was quadratic in n? Now, we said that if it was linear in n, that if you double the number of data points, what happens to the time? It doubles. But if it's quadratic in n, and you double the number of data points, what happens to the time? 4 times, because it's quadratic. Does everybody see how that works? Okay, so this is how we interpret those asymptotic bounds. And now there is a theorem here. All these techniques that we are using can be generalized, and you can generalize it to an arbitrary polynomial, and it's called this polynomial bound. And the thing of it is that if you have something like this, 53n to the 5th minus 4,000 n cubed plus 23n squared minus 100 million thousand whatever. You can know right away from this theorem that this is what? That this equals big theta of what? Is all you have to do is just look at what? All you have to do is just look at this. And this theorem says that this is big theta of n to the 5th. Because you can do all this, drop the positive, increase the negative, provided n is greater than or equal to blah, blah, blah. You can do that to all these coefficients and eventually collapse it all to this. All right? So this is the only one that matters. Right? As long as it's positive. The leading coefficient has to be positive. See? A sub d is greater than 0. That's the leading coefficient in that expansion. All right? But, so theoretically, you could just quote this and not go through those individual proofs. But I want you to be able to, we need to be able to prove from the definition. Okay? So that we have a feeling for what these asymptotic bounds are. Okay, well, it sounds like I see a lot of nodding heads. So, I mean, yes, not sleeping. So it sounds like you guys we're all together on this. Now this next topic is how to analyze recursive algorithms. Now, when we did the statement execution counts, we did statement execution counts with loops, right? And you figure out what this index is, and it's this many times, you add them all up. But think about this. Here's the problem. Suppose you have a recursive algorithm. Now, what is a recursive algorithm? It's an algorithm that does what? That calls itself. Now, how are you going to count how many statements execute?
Oh, with trees?
You see, well, it gets tricky.
Use factorial?
Well, no, I mean, that's our problem. Our problem now is to be able to analyze algorithms that call themselves. Okay, so these are recursive algorithms, all right? Now, in order to do a statement execution count for a recursive function, what we have to be able to do, the first step we need to be able to do is we need to be able to write what is called a recurrence. We need to be able to write a recurrence. And what we need to be able to do is write it by inspecting the code, inspecting the recursive code. Now what we have on this slide is the general shape of a recursive algorithm. So you guys have all done towers of Hanoi and all that stuff, right? And you know that when you do a recursive algorithm, how does it always work? If, what? The base case, yeah, the smallest one. Then you do some computation with no recursive call. Else, what do? You have one or more recursive calls with possibly some additional computation. Is everybody clear? So you've seen, this is the shape of a general recursive algorithm. All right? Now, here's what we have to be able to write down. We have to be able to write down the recurrence for this. And the recurrence always has this shape. It's the same as the shape of the code. It mirrors the shape of the code. Now, it doesn't say on this slide, but let me write down what T of n is. T of n is the time to execute for a value of n. It's the time to execute when the problem size has, like n could be the number of data points for n data points. All right? And what it's equal to is, in the same way that there's a base case and a recursive call, there's two parts to the recurrence. So what T of n equals is, it equals to the count for the smallest problem, if it's the smallest problem. On the other hand, otherwise, what is it? Otherwise, it's the count for the recursive calls plus the count for any additional computation. Now let's just think about that for a minute. Because look, if it's going to call itself, then this expression, when it calls itself, it will be for a slightly smaller problem. But this T of n still is the time to execute for a value of n. Okay, so let's close with this example. So first, writing recurrences. To determine the statement execution count is a two-step problem. First, you write down the recurrence from the recursive code for the algorithm, and then second, you solve the recurrence. So it's two steps. So what we're doing is the first step. We are writing down the recurrence. Now let's do it for this example. Here's a little pseudocode for the factorial of n. Now watch this. The factorial of n. Now, do you agree that this code, you've probably written this program before, haven't you? If n is less than or equal to 0, then return 1, else return n times what? Factorial of n minus 1, right? This is pretty simple. Okay. Now the question is, what's the statement execution count of this? Well, the first step we have to do is we have to write down the recurrence. So here's how we write down the recurrence. This is the recurrence. Its T of n is 2 if n is less than or equal to 0, and its T of n minus 1 plus 3 if n is greater than 0. Now where the heck did this come from? Notice that the recurrence has two parts to it, just like the code does. All right. Now where did this come from? Look. Where did this 2 come from? Well, if n is less than or equal to 0, what statements execute? The if statement and the what? The return 1. So you see, that's where the 2 comes from. Now, if T of n is the time it takes to calculate the factorial of n, then how much time does it take to count the factorial of n minus 1? Here, if T of n is the time to calculate the factorial of n, then how long does it take to calculate the factorial of n minus 1? T of n minus 1. So look, this factorial n minus 1, that's where this T of n minus 1 comes from. Now does everybody see that? So this is see, this is t of n defined in terms of t of n minus 1. But this comes from this. This t of n minus 1 comes from this factorial call. But now, after it does that factorial call, then what does it have to do? It has to multiply. It has to, oh, and by the way, how did it get there? If n was that, so that if statement had to execute, then it had to multiply, and then it had to execute the return. So that's like 1, 2, 3. So that's like plus 3. Does everybody see that? Yeah.
So the multiplication there is an additional computation.
Yeah, you know, that's a good question. The multiplication is an additional computation. But look, we can write it this way, but what do we know about 2? What is 2? 2 is big theta of what? Do you agree that 2 is big theta of 1? And do you also agree that 3 is big theta of 1? So whether it's 3 or whether it's 5 or whether it's 2, it's what? The constants are what? All constants are what? Big theta of 1. So another way of writing this is say, you know, we can just write it this way, and whether you count the multiplier or not, it doesn't really matter in the long run. All right? So we'll close with this example. Any questions? Any more little questions here at the end? Okay, good deal. See you tomorrow.